These are the answers to homework 1F. These are the definitions I would like you to know. Now let's go to the questions. Number 1, for the following acids, write the reaction for their ionization in water and their acid ionization constant expression. The Bronsted-Lowry definition of an acid is something that donates a hydrogen ion, and in a water solution, it would donate it to the water molecule itself. For A, HClO2 plus H2O is in equilibrium with H3O plus ClO2 minus. Equilibrium constant expression for this, Ka equals molarity of hydronium ions multiplied by molarity of chlorite ions divided by the molarity of chlorous acid. B, HCN plus H2O is in equilibrium with H3O plus Cn minus. Equilibrium constant expression, Ka equals molarity of hydronium ions multiplied by molarity of cyanide ions divided by the molarity of hydrocyanic acid. C, HCO2H plus H2O is in equilibrium with H3O plus HCO2 minus. The acid in this one is formic acid. It's an organic acid. And as we've seen, organic acids have a hydrogen that can be ionized because it has a carboxyl group on it, the CO2H unit. The hydrogen that's bonded to one of the O's is the one that gets pulled off when the substance acts as an acid. And so that's why the formate ion on the product side is written HCO2 minus, indicating that it's the very rightmost hydrogen, the one bonded to O, that actually gets ionized, making the substance an acid. The Ka expression, molarity of hydronium ions multiplied by the molarity of formate ions divided by the molarity of formic acid. Number 2, from data on handout 3, rank these acids from weakest to strongest. 3 of these acids have values for their Kas given on handout 3. One of them didn't, that was water. And we talked about this in lecture. When water acts as an acid, the reaction is water plus water yields hydronium plus hydroxide. And the equilibrium constant for that reaction is known. It's 1.0 times 10 to the minus fourth. So comparing that with all of the other Kas, whichever acid has the smallest Ka value, that's going to be the weakest acid. And so therefore, water is the weakest acid out of these 4. The first one had the second lowest Ka value. It's the second weakest. The ammonium ion had the third lowest. It's the third weakest. And the fourth weakest or the strongest acid is the HClO2 because it has the largest Ka value. Number 3, for the following bases, write the reaction for their ionization in water and their base dissociation constant expression. The Bronsted-Lowry definition of bases are substances that accept a hydrogen ion, and so in water solutions, they accept a hydrogen ion from water. For A, the reaction is CH3NH2 plus H2O is in equilibrium with CH3NH3 positive plus OH minus. I've added the hydrogen onto the end of the compound because it's the nitrogen that actually has a lone pair on it that a free hydrogen ion can bond to, and so it actually bonds to that nitrogen. Kb expression, molarity of CH3NH3 positive multiplied by molarity of OH minus divided by molarity of CH3NH2. B, F minus plus H2O is in equilibrium with HF plus OH minus. Equilibrium constant expression, it's a Kb because the fluoride ion is acting as a base, it's gaining a hydrogen. Kb equals molarity of HF multiplied by molarity of OH minus divided by molarity of F minus. C, NO2 minus plus H2O is in equilibrium with HNO2 plus OH minus. Equilibrium constant expression, Kb equals concentration of HNO2 multiplied by concentration of OH minus divided by concentration of NO2 minus. Number 4, for the following acids, rank them from weakest to strongest. And the 4 acids I gave you did not have Ka values given in handout 3, so I wanted you to predict this based upon your knowledge of their strengths. We've learned that the more O's there are related to H's in an acid, the stronger the acid. And the top one has 2 more O's than H's in its formula. That has to be the strongest acid. Now, the question says if once we've ranked them, that's the strongest, then HBRO2 has only 1 more O than H, that's going to be weaker, and HBRO has no more O's than H's, that's the weakest. So HBRO, the weakest acid, then HBRO2, and then this would be the strongest. B says predict the numerical value for their acid ionization constants. So if you have a strong acid, what does that mean? 100% of the acid molecules lose their hydrogen ions. So you would have lots of products in the solution and you would have essentially no reactants. That's a big number over 0. That's technically the value of infinity. So strong acids should have Ka values of infinity, but if some of them don't completely ionize and only 99.999% ionized, then at least you can say that the Ka is going to be a really big number. I would expect you to predict something like 10 to the big positive number. The other two are classified as weak acids. Weak acids do not ionize very much. You don't get very many products. The acid molecules stay bonded together mostly, so the Ka value would be the fraction of a small number over a big number. It would have to be a value that's 10 to a negative number. Whatever you put there would be perfectly acceptable for the Ka for HbRO2. Then, because HbRO is a weaker acid, that means its Ka value must be smaller than whatever you had for HbRO2. So whatever you had for HbRO2, as long as what you put for HbRO is smaller than that, then I would mark that right. Number 5, calculate the pH of each of the following strong acid and base solutions. A is a 0.100 molar solution of HCl. In water, HCl would donate its hydrogen ion to a water molecule, forming a hydronium and a chloride ion. So if we're starting with 0.001 molar HCl, and we're assuming there's nothing else in the solution before it reacts, because it's a strong acid, it all reacts away. You'll therefore form in a 1-to-1 ratio 0.001 molar of hydronium and 0.001 molar of chloride, and so therefore you'll have 0.001 molar of hydroniums in the solution. The negative log of the hydronium concentration is your pH, so you just take the negative log of 0.001. That's a 1 significant figure number, so your answer is going to be, as a logarithmic value, 1 digit past the decimal point. That comes out 3.0. B, calculate the pH of a 0.02 molar HNO3 solution. HNO3 is a strong acid at 100% ionizes, and without writing out an entire ICF table, if I recognize there's only one hydrogen in the formula of HNO3 and it all ionizes, you will get 0.02 molar of hydroniums and 0.02 molar of nitrates because there's one hydrogen and one nitrate in the formula. So therefore, by inspection, I know the molarity of the hydroniums will be 0.02. So to calculate the pH, I'm just going to take the negative log of that number, and 0.02 is a 1 significant figure molarity, so my logarithmic pH will have 1 digit past the decimal point. The pH will be 1.7. C is 0.001 molar sodium hydroxide. This is a base, and when you have an ionic compound that's a base, a metallic hydroxide, the reaction that produces the hydroxide ions is just the ionic compound dissociating into ions. So the sodium hydroxide will dissociate into a sodium ion and a hydroxide ion. They told you you're making the solution 0.001 molar in sodium hydroxide. Nothing else is in there first. So if all the sodium hydroxide dissociates, and this is what soluble ionic compounds do, they dissociate completely, it will all dissociate, creating in a 1-to-1 ratio 0.001 molar of sodium ions and 0.001 molar of hydroxide ions. So therefore, there are 0.001 molar of hydroxide ions in the solution. When you know the molarity of hydroxide ions, that will allow you to calculate the pOH of the solution, not the pH. So the negative log of 0.001 will give you the pOH of the solution, which is 3.0. If you mistake that for the pH, this shouldn't make sense because that value is less than 7, and we know pH is less than 7 are acidic. Well, this is a pOH. To get the pH, you use the relationship pH plus pOH equals 14. And so we can solve for the pH by going 14 minus 3, and that will give us a pH of the solution, which is now above 7, a basic value, 11.0. In D, we have 0.001 molar barium hydroxide. Now, barium hydroxide, when it dissolves in water, completely dissociates, and you had to recognize here that when it dissolves, you form 1 barium ion and 2 hydroxide ions. So if 0.001 molar of barium hydroxide is dissolved in water and it all dissociates, a 1-to-1 ratio, you'll form 0.001 molar of barium ions, but it's a 1-to-2 ratio, you're going to get 0.002 molar of hydroxide ions formed, and so the solution will actually be 0.002 molar in hydroxide ions. To calculate the pOH, we take the negative log of this number, and we get to one significant figure, or one place past the decimal point, 2.7, and that's your pOH. The pH is calculated by going the pKw, which is 14, minus the pOH of 2.7, and that'll give us a pH of the solution, which is on the basic side of 7, of 11.3. Number 6, the acid ionization constant for arsenious acid, HASO2, is 6.0 times 10 to the minus 10th. A, calculate the pH of a 0.10 molar solution of arsenious acid. So to calculate the pH of a solution, we need to know what the hydronium ion concentration is. And if it's a weak acid, we're going to have to calculate this from its Ka expression, which comes from the reaction of the acid ionizing with water. So when arsenious acid reacts with water, it forms a hydronium ion and the arsenite ion, ASO2-. If we do an ice table, we're starting with a solution that was originally 0.10 molar in arsenious acid, and we'll assume there's nothing else present. Because it's a weak acid, all of it doesn't ionize, some unknown amount does. We use the coefficient in the balanced equation to say 1x of it ionizes, and you're going to form 1x of hydronium and 1x of the arsenite ions. Equilibrium molarities will be 0.10 minus x, x and x. And these equilibrium molarities are related to each other through the Ka expression. Ka equals hydronium ion molarity times arsenite ion molarity divided by arsenious acid molarity. If we know the Ka, we can plug the equilibrium values into the expression and we can solve for the one variable. You either solve this by doing the quadratic equation, or because the Ka is so small, you can assume that an x subtracted from 0.10 is going to be really small compared to 0.10, and we can solve this instead. We're essentially making the assumption that x is really close to 0. If you solve this for x, x comes out 7.8 times 10 to the minus 6th. And if you want to verify that that was a good assumption, that the x will be close to 0, we're going to take x and divide it by 0.10 and multiply it by 100 to see if that's less than 5%. So my x value divided by the original concentration of the arsenious acid times 100 equals 0.0078%. So that means this was a really good assumption. X is really, really small. So we can assume that x is 7.8 times 10 to the minus 6th. Now that's the hydronium ion concentration in the equilibrium line of the ice table. So if we just take the negative log of the 7.8 times 10 to the minus 6th, that'll give us the pH of this solution. And to two significant figures, we write two places past the decimal point, comes out 5.11. Part B says, what's the pOH of this solution? If we know the pH, we'll get the pOH, excuse me, by going pH plus pOH equals 14. So solving for the pOH, it's going to be 14 minus 5.11. So the pOH of the solution should be 8.89. Number 7. A 0.10 molar solution of trichloroacetic acid is 1.3% ionized. A, calculate the Ka for the acid. The Ka is the ratio of the molarity of the products to the molarity of the reactants at equilibrium. So we have to know the equilibrium molarities of all the components in the solution. So we're going to write the reaction that an acid undergoes when it gets dissolved in water. So the trichloroacetic acid will react with water to form a hydronium ion and then the anion CCl3CO2-. We can write an ice table to predict the equilibrium molarities. We were starting with 0.10 molar of the trichloroacetic acid, and there wouldn't be any ions present before it ionizes. It's a weak acid, so therefore a small amount of it ionizes. And we know it's a weak acid. It said it only 1.3% ionizes. It didn't say 100%. So some small amount of it ionizes, and some small amount of each of these are formed. The equilibrium molarities will be 0.10 minus x, x and x. And those equilibrium molarities are related to each other through the equilibrium constant expression. So the molarity of the hydroniums times the molarity of the trichloroacetate ion divided by the molarity of the trichloroacetic acid, that ratio will equal the Ka, which we're going to try to solve for. Now the equilibrium values we have are all in terms of x, so you have a situation where you have two variables. So we have to have a clue in the problem to allow us to calculate x before we can get the Ka. And that clue was the fact that this acid is only 1.3% ionized. So what does that mean? That means the amount that dissociates or ionizes, which in the ice table under the trichloroacetic acids in the change line, X, divided by the original amount, 0.10, multiplied by 100, has to equal 1.3%. So if we use this relationship, we can solve for X, and X turns out to be 0.0013. So now we can place 0.0013 in place of all the X's in our Ka expression. We don't assume the X in the denominator is 0. That would just introduce error to the problem. We put the values actually in as long as we know them. And now you can calculate the Ka, which comes out 1.7 times 10 to the minus fifth. Part B says calculate the pH of the solution. The pH of the solution comes from the hydronium ion concentration, which was X. And X is 0.0013. So if we take the negative log of 0.0013, that's going to give us the pH of the solution. And to two significant figures, that comes out 2.89. Number 8, a 0.25 molar solution of iodous acid has a pH of 3.47. A, calculate the Ka for the acid. So just like the previous problem, we need to know the ratio of the equilibrium molarities of the products to the equilibrium molarity of the reactants. And all we're given is an initial molarity of the iodous acid, so we're going to have to figure out what the equilibrium molarities are by writing the reaction of iodous acid ionizing in water and then writing an ice table. So iodous acid would react with water to form a hydronium ion and an iodite ion, and the ice table would start with the initial concentration of the iodous acid, and there would be no products before it reacts at all. The change would be an unknown amount because it's a weak acid, so we'd say minus X and then plus X and plus X. Equilibrium molarities would be 0.25 minus X, X and X. And those are all related to the equilibrium constant, the Ka, through the Ka expression. If equilibrium values and plug those into the right side of our Ka expression, we now have an equation that allows us to calculate Ka, but we have a second variable, X, and we have to figure that out first. So there has to be something in the problem to allow us to get X. And the clue is they say the pH of the solution is 3.47. The pH of the solution is related to the hydronium ion concentration. And in this solution at equilibrium, the hydronium ion concentration is X. So if we take our definition of pH, pH equals negative log of the hydronium ions, and we solve it for the hydronium ions, the hydronium ion concentration equals the antilog of the negative of the pH. So if we take the antilog of negative 3.47, we'll get our hydronium ion concentration. Now 3.47 is a logarithmic number. Only the 4 and the 7 are significant figures, so that's a 2 significant figure number. So when we actually calculate the molarity of the hydronium ions, now we have to express this as a normal 2 significant figure number, which would be 3.4 times 10 to the minus fourth, or with a guard digit, 3.39. This is the hydronium ion concentration, and then from the equilibrium line in our ice table, the hydronium concentration is X, so this number equals X. So if I just replace X in my Ka expression with 3.39 times 10 to the minus fourth, we can calculate the Ka of the acid, and to two significant figures, it comes out 4.6 times 10 to the minus seventh. Part B says calculate the percent ionization of iodous acid, and this is done by taking the amount of iodous acid that ionized, which is in the change line on the ice table under HiO2, that's X, dividing it by the initial amount, 0.25, and then multiplying it by 100. So the X value was the 3.39 times 10 to the minus fourth, divided by 0.25, multiplied by 100, and to two significant figures, this is a very weak acid. Its ionization percent is only 0.14%. Number 9, the base dissociation constant for the organic base pyridine is 1.58 times 10 to the minus eighth. A, calculate the pH of a 0.10 molar pyridine solution. So if we're going to calculate the pH of a basic solution, we're going to actually figure out the hydroxide concentration, get the pOH, and then figure out the pH from that. So when bases react with water, the reaction is the bases accept the hydrogen from water. So this is the most important thing for you to be able to do correctly with a base. The correct reaction with water is that the base reacts with water, pulls a hydrogen off of the water. the hydrogen actually bonds to the nitrogen in the base to form C5H5NH+, and the water is turned into a hydroxide ion. For weak bases, we get our equilibrium established, and now the concentration of the hydroxide ions at equilibrium can be determined from an ice table. The original pyridine concentration was 0.10, and we'll assume that before it ionizes, there aren't any products in the solution. If it's a weak base, some unknown amount of it will ionize, forming in a 1-to-1-to-1 ratio, X amount of the two products. The equilibrium molarities will be 0.10 minus X, X, and X. And these equilibrium molarities are related to the Kb through the equilibrium constant expression. So the base dissociation constant is going to equal the concentration of C5H5NH positive multiplied by the concentration of OH minus divided by the concentration of C5H5N. In this case, we know the value of the Kb, 1.58 times 10 to the minus 8th. That will equal from our equilibrium line x squared over 0.10 minus x, and we can solve for x. You can do it exactly by using the quadratic equation, or because the Kb is less than 10 to the minus second, you can assume x will probably be small compared to the original molarity of the pyridine. And so I'm going to assume that x in the denominator is so small it's essentially 0, and I'm going to solve this equation instead. When I do, I get x equal to 4.0 times 10 to the minus 5th. And if you want to verify that that was a good assumption and that this x value must be small, must be less than 5% of the original pyridine concentration, you take the value for x, divide it by the original amount, multiply by 100, and you verify it's less than 5%, and this is way less than 5%, so this was a good assumption. So that just means we can assume that x is 4.0 times 10 to the minus 5th. Now, X stood for, in the equilibrium line, the hydroxide concentration. So from the hydroxide concentration, if we take the negative log of it, we're going to get the POH. So using a guard digit, the negative log of 3.97 times 10 to the minus 5th, and it comes out as a two significant figure number, 4.40. That can't be the pH. That's an acidic pH. This is a base. You've calculated the POH. So the pH is going to be 14 minus the POH, which comes out 9.60. Part B says calculate the concentration of the C5H5NH positive ion in this solution. If you look at the equilibrium line, the answer is right there. At equilibrium under C5H5NH plus, it says X. So that means whatever X was, that will be the concentration of that cation in the solution at equilibrium. And so it just equals 4.0 times 10 to the minus 5th molar. Number 10, the base dissociation constant for the weak base hydrazine, N2H4, is 2.0 times 10 to the minus 6th. Calculate the molar concentration of hydrazine that would yield a POH of 3.52. They're asking you for the concentration of hydrazine so that when the solution reaches equilibrium, the POH is 3.52. This problem is different from all the previous ones because you're not being asked to solve for an equilibrium molarity. You're being asked to solve for an initial molarity. What has to be the concentration of hydrazine you put in there initially so that eventually when you reach equilibrium, the POH is 3.52. You're going to figure this out by writing the reaction for hydrazine acting as a base because they tell you it's a weak base. And the reaction it undergoes is with water. When any base reacts with water, it takes a hydrogen from water. So the hydrazine would take a hydrogen from water and form N2H5+. The water would turn into a hydroxide ion. We do not know the initial concentration of the hydrazine. That's what it wants to know. I've called that A in previous problems. I'll call it C here. You can use whatever variable you want. So we'll assume we have some concentration of hydrazine and it hasn't reacted yet. Some small amount of that will ionize, and you'll form X amount of the cation, X amount of hydroxide. So the equilibrium molarities will be C minus X, X, and X. Those equilibrium molarities are all related to the Kb for hydrazine through the Kb expression. Concentration of C2H5 positive multiplied by the concentration of OH minus divided by the concentration of N2H4. In this case, we know the Kb, it's 2.0 times 10 to the minus 6th, and that's going to equal X squared over C minus X. We're trying to find C, but we have this X variable in there that we have to figure out first, so there has to be some clue in the problem that lets you figure that out. And the clue that was given is the pOH is 3.52. The pOH is related to the concentration of hydroxide ions, which is X in the equilibrium solution. So if we take the antilog of the negative pOH, that will be our hydroxide concentration, that will be X. So the antilog of negative 3.52, and 3.52 is a logarithmic number, so only the 5 and the 2 are significant figures, so that's a 2 significant figure number. So when I get my hydroxide molarity, I'm going to write it as a natural 2 significant figure number, 3.0 times 10 to the minus 4th, and the 2 is just a guard digit. So that's the value of the hydroxides, which stands for X. So in the equation, all places where the X appear, you substitute it for 3.02 times 10 to the minus 4th. If you can solve this for C, that will be the initial concentration of hydrazine you would had to have started with, so that the solution winds up with a pOH of 3.52, and that turns out to be 0.046 molar.